Welcome to lesson 15 of our friendly introduction to abstract algebra. This week's lesson we are talking about cosets. What is this? So we take, of course, G is a group and H is any subgroup of this group and G any element of G. Then we define the left coset, of course, with respect to H to be the following set. G times H, meaning exactly this. We take all the products of G with all the elements of H. This clearly is a subset of G, but be aware it need not be a subgroup. We're going to see that in a minute. And similarly, the right coset is defined like that. Simply take the products HG, where H runs through the whole subgroup. And in this course, unless otherwise specified, coset will mean left coset, because we mostly or almost always work with left cosets. Now, the example that we already know, only in another terminology, we take the integers, and as a subgroup we take n times the integers. N, any natural number. Well, for 1 it is trivial, so we start with 2 maybe. Now, if G is any integer, then we do not write GH as here, because we are in an abelian group that is written additively, so we write G plus H. So here is always the operation in the group. This is why here you could write G dot H, but I mostly write simply GH. What is this? By definition, this consists of all these elements, G plus H, H running through the whole subset NZ. So H is of this form here, k times n, integer multiple of n. But we already know this set. This is nothing but the residue class of G mod n, which we abbreviate by G bar, or G overline. And since Z is an abelian group, I could switch the order here and would end up with the right coset. So in abelian groups, those are the same. And now here we already see that such a coset need not be a subgroup, so subgroup sign cancelled, durchgestrichen, crossed out. Sorry, words fail me. If G is not congruent to 0 mod n, then clearly the number 0 is not an element of this coset here, because I cannot end up with 0 if G is not congruent 0 mod n. And then this can't be a subgroup, because every subgroup must contain the identity of the group, which in this case is 0. Now, a non-abelian example, and it's very, very important whenever there's a new definition to take some small examples, some small groups that you know well, and just figure out what this here means in this nice little context. And just figure out by writing down some cosets with a few elements. So we take the subgroup generated by a transposition 1, 2 in S3, the permutation group on 3 elements. This here consists only of 2 elements, because tau squared is already the identity. That's the nature of a transposition. As our fixed element G, in this case we call it gamma, we take a 3 cycle, 1, 2, 3. And now we take a look at the left and the right cosets. Gamma H, the left coset, is by definition gamma composed with all the elements of H. But there are only 2, so this is gamma composed with the identity and gamma composed with tau. And this clearly is gamma itself. And this here gives the transposition 1, 3. Please pause the video and think about that for 10 seconds. Just look at here. These permutations. Now the other way round, it composed with gamma clearly stays gamma, but now here, because those 2 elements do not commute, I end up with the transposition 2, 3. So left and right coset are not the same. So when working in non-abelian groups, you have to be careful about switching the order of the coset. Okay, ideally you have watched the videos for lesson 6 and did problem set 6, so you are well acquainted with equivalence classes and partitions. If not, I would highly suggest that you go back and do that, because we will need that now. So here I'm assuming that you are not so familiar, so I'm a bit redundant in what I'm saying here. So we have the following lemma. As always, H is a subgroup of G and X, Y are arbitrary elements of G. Now, the following three statements are equivalent. First statement, the left coset of X is equal to the left coset of Y. Second statement, Y lies in the left coset of X. And third statement, X inverse Y lies in H. This proof is left as an exercise. I would suggest you do it in two ways. First way, really do this from scratch, by hand. Second way, look again at problem set number 6, especially this exercise. There we had the inverse here, we had AB inverse. So this would correspond to the right cosets, but that doesn't matter. It's of course the same idea in the proof. And then you already know that this here defines an equivalence relation on the whole group. And then this should become clear without any further work, because the equivalence class is simply the left coset, or in the case of this problem, the right coset, but again, that does not matter. So I would suggest you do it in two ways, thereby reviewing what equivalence relations and equivalence classes are. So, one special case is so important that I will note it as a corollary. So a warm shout out to the kind college music professor from the US who once corrected me. I used to say corollary, but this seems to be the UK, the English pronunciation, so it should rather be corollary. So we have a corollary. What does that mean? Lemma. That's a statement that does not deserve to be called a proposition, but it is so useful that we still write it down and give it a name. This is what we call a lemma. And corollary is just a simple special case or follows immediately from something we just proved before. So the corollary is the following. GH equals H if and only if G is an element of H. Of course, for H a subgroup. And similarly for right cosets. So if HG is H, then if and only if G is an element of H. Why is this a corollary? Corollary, damn it. Why is this a corollary? Because simply set X equals the identity and Y equals G, then here we have H is equal to GH, exactly that. And by this lemma, this is equivalent to this statement here, but if X is the identity, we simply have G. So G element H if and only if the left cosets here are the same, so GH equals H. That's why it's called a corollary. All right, so let's take a look at what this statement really means in the context of the group being the integers and the subgroup being NZ. Here we write X inverse Y as minus X plus Y because it's an additively written group, so the inverse of X is minus X and the addition, the operation is addition. So this here means that this here holds, but this means that minus X plus Y is of the form K times N for some integer. I always write this as NZ, not Zn, but here I like Kn better than n times k because somehow the k should be in front like 3n and not n3, n times 3, whatever. So, but this means that y can be written like this, x plus kn, but then it obviously lies in this coset here, or what we call the residue class, mod n. So, this here means, in this notation, nothing but our well-known equivalence relation on the integers. Two numbers are equivalent mod n if and only if their difference is divisible by n. Or in other words, is an integer multiple of n. At the latest point now, I would encourage you to revisit lesson 6, where we talked about equivalence relations and partitions. Because then this all here becomes self-evident. Now we make the following definition for a subgroup H of G. We define an equivalence or a relation. X is related to Y if and only if this here holds. So exactly this condition from the lemma. or from problem set number 6, then this is an equivalence relation, and the equivalence class is exactly the left coset of X with respect to H. Furthermore, remember, each equivalence relation gives rise to a partition of the set. So imagine the group like that. And then here we have the left coset of the identity, which is simply H. And then we have some other cosets. And now the group can be sliced up into all these different disjoint cosets. This is what we call a partition. Now we assume that G sub I running through some index set capital I, is a complete system of representatives of the cosets, meaning that for every existing coset I pick exactly one representative, and then G can be written as the disjoint union of all these cosets where I runs through this index set I. And well, by the above lemma and lesson 6, there's nothing left to prove, because you can easily check, or you have already checked here on this problem set, that this defines an equivalence relation, and then it is clear because of this here that the equivalence classes are exactly the left cosets, because if X is equivalent to Y, it means this is equivalent to Y lying in this set. So by definition of equivalence class, this set here is the equivalence class. So every subgroup of a group gives rise to a partition of the group. This is a very, very important statement. Okay, if you're feeling a bit overwhelmed and this was too abstract, fear not. Here comes an easy example. We take the integers mod 6 as our group. So the group consists of these 6 residue classes, 0 bar, 1 bar, up to 5 bar, 6 bar, again, or the congruence class of 6 is 0 bar. And as a subgroup, we take the cyclic group generated by 3 bar. In additive notation, these are all the multiples of 3. 0 times 3 bar is 0 bar. 1 times 3 bar is 3 bar. 2 times 3 bar is 3 bar, plus 3 bar is 6 bar, is again 0 bar. So this subgroup consists of 2 elements. And now we, by brute force, write down all the left cosets. We take all the elements. Here we start with 0 bar. 0 bar plus H is by definition the set consisting of all these expressions, 0 bar added to these here. And this, of course, gives me H itself. And this is the same as 3 bar plus H, because 3 bar plus 0 bar is 3 bar. 3 bar plus 3 bar is 6 bar, which is 0 bar. And the same here. The left coset of 1 bar is the same as the left coset of 4 bar, and the same for 2 bar and 5 bar. So there are 2 ways to partition the group. The first way would be to take these here. Clearly, they are disjoint, and the union gives the whole group. This is clear because we have an equivalence relation on this group, but here you see it with your own eyes. So if you take the union of these, you get the whole group, or you could take the union of these here, they are the same. Again, you get the whole group. So those are 2 different partitions, but the index set in both instances has order 3, because of course we have the same sets here. And now the order of the index set, in this case 3, is called the index of the subgroup. So this here would be a subgroup of index 3. The order of the subgroup is 2, it has 2 elements, but the number of disjoint cosets is 3, and this is what is called the index. And let's define this for a general group. If H is a subgroup and G can be written disjointly as the union of these left cosets, capital I being a complete index set of a complete representative system, then the index of this subgroup in G, more precisely the left index, but we always talk about left cosets, and on this problem set you will show that left and right index are the same. written like that, G colon H in these brackets here. This is called the index of H in G, and by definition this is the order or the cardinality of this index set, which corresponds exactly to the number, or is the number of disjoint left H cosets. Okay, to look at a trivial example, the index of G in itself is always 1. Why? Well, the left coset of the neutral element, e.g., of course, gives me all of G, so there's only one left coset. And you could take any element here. So any element gives rise to the same coset G itself, so the index is 1. What is the index of the trivial subgroup consisting only of the identity in G? Well, this is exactly the order of G. Why? Take a look at the left cosets. G times the trivial subgroup, of course, is this singleton set consisting only of G. And if I take the union of all these sets, then of course I end up with G itself. So there are order of G many left cosets, and this is exactly what this statement here means. Now, a non-trivial example would be the index of nz in Z, which is clearly n, because there are n different left cosets, which we back then called residue classes. K runs through 0 up to n minus 1, n different possibilities for these cosets, so the index is exactly n. Or in the example above here, in our new notation we would write the index of this subgroup in Z6 is 3. All right, that is lesson 15. As always, take your time to get acquainted with the new concepts here, do some of the exercises on problem set 15, and I hope to see you in the solution videos or in next week's lesson where we learn about Lagrange's theorem, one of the first real propositions about the structure of groups, or in this case, not the structure, but the possibility of the order of subgroups. All right, have a good one and bye-bye.